Hi, I'm Cole.
Hi, I'm Selma.
Hello, I am Josh.
Hey, I'm a boss.
And we're going to take the time to explain the process of orthonormalization.
Through the Graham-Schmidt process.
Yeah.
Hey guys, I'm going to be covering some of the basics of the Graham-Schmidt process. There are two things that we need to cover prior to talking about the actual orthonormalization. The first thing is orthogonal, in which the inner product of two vectors in your set are equal to 0, and then normality, in which you divide the vectors by their norms in order to establish a unit vector, which is much easier to work with. Next, we have the geometric representation of your Graham-Schmidt process, in which you have W1 and V2. And essentially, in order to find W2, the resultant vector that you're looking for, you subtract V2 minus V2's projection onto W1. And this resultant vector is orthogonal to W1. Next, I just wanted to show the algebraic representation in which W2 is equal to V2 minus V2's projection onto W1. And then here we have the general form in which Wn is equal to Vn minus Vn's projection to all the different vectors that you have in your set. And then finalize, in order to finish this, you need to normalize said vectors and put them in a basis. And with this, you can further your understanding and usage of the Graham-Schmidt process.
Hey guys, I'm going to show an example of the Graham-Schmidt process. So we've got our original set of vectors here with V1, V2, and V3. So we're going to begin by setting W1 equal to V1. We now need to find W2. So we're going to take our V2 and subtract the projection of V2 onto W1. From that, you work out the numbers and you get that 0, 1, 1 is equal to W2. Now we need to find W3. So we take our vector 3, subtract the projection of vector 3 onto W1 minus vector 3 onto W2. We get this equation, and you solve that out, you get 0, 1, negative 1. That's your W3. We now need to find the normal vectors of our W's. So your normal vector 1, or U1, is your W1 over the magnitude of W1, which ends up being the same thing. Your U2 is going to be W2 over magnitude of W2, which is going to get you 0, 1 over square root of 2, 1 over square root of 2. That's your normal vector. And then U3 is going to be W3 over magnitude of W3, and that will get you 0, 1 over square root of 2, negative 1 over square root of 2. So you take your normal vectors, and that is your orthonormal set, which is orthogonal. They're all orthogonal to each other, and they're all unit vectors.
So I'm going to talk about some applications for the Graham-Schmidt process. One application for the process in our everyday life is in finding out natural vibrations. A quick definition for the natural vibrations is the frequency of a system with no driving or damping forces. This can see use in the planning of buildings and structures, because if you don't consider the natural vibrations, then the buildings may not be stable. And in the context of music, knowing the resonances of the instruments themselves allows you to hit certain tones.
The Graham-Schmidt process is related to the natural vibration of objects through a series of theories. First, we can use it to find an orthonormal basis, and that allows us to find the use of operators in inner product space, which allows for diagonalization and relating the diagonal matrix with the original using something called spectral theory, which reduces the diagonal matrix components. And after we find all that, namely the diagonalization, it allows for knowing something called the eigenvalue, which in a transformation is a value that can be multiplied by a vector without changing the transformation. And all of that relates to these two equations, which are equations for the vibrations of an object. And this equation relates the mass matrix and the acceleration vector with the stiffness matrix and the displacement vector, which is sinusoidal, which can be reduced to this side times the angular velocity squared times mx, which x comes from here. And in this equation, w squared, or the angular velocity squared, is our eigenvalue obtained here, which we need the orthonormal basis to achieve. And that's how the Graham-Schmidt process can be applied to find the natural vibrations of an object.